I think I will start because it will take long time. So this is going to be some warm-up review. The first session is going to be some warm-up review on some useful concepts of physics that are applicable in doing radio astronomy. So actually 8 lectures may not be sufficient for this, but I will stop for 8 lectures as I have already said in the notice. Out of which I don't know how many can be covered this time. If some of the things that are left, then that will be covered in the next time. So this is what is the scenario. Today you have lecture number 1. And for textbook, if you want to see, you can follow any radio astronomical textbook. If you want to do, if you want to understand more. But I will follow what I have written. And this is for anybody who has a background of science or engineering can follow my lectures. And the book that I am following is this one. This is yet to come out. This is written by me. They have not yet put it in the market. I think it is still under, I don't know what is the status now. And then Indian edition will also come out. So I will just go through the, I will review the basic concepts of physics that are applicable for radio astronomy. And these things will help you to understand things like coherence, visibility, fringe, and electromagnetic waves, polarization. So these are not the actual things. The actual things are more difficult. But in order to make them more easier, I thought that it is better to give some background for this so that people can understand. There is also one book in the library that is actually I took that edition out for corrections and proofreading, so it may contain some mistakes. If you want, you may refer to that also. So actually, most of the things people know about it, but I will just go through it and I will do it fast because there are about 69 slides in this one. So I don't know whether I will be able to cover it up in 2 hours. So I will try to go as fast as possible. And if any people has got any doubts, I don't think people will have any doubts in this. These are very basic things. If it is a time-consuming thing, so then I will take it up after the class. But if it is small questions, I will answer it there. So we move on to this one, this laws of universal gravitation founded by Newton. And here it says that every object attracts every other object with an attractive force, which is directly proportional to the masses and inversely proportional to the square of separation between them. That is, if these are the two masses, having m1 and m2 are the masses, and these are the vectors that are drawn. This vector is directed towards this one, and this vector is directed towards this one. That means if you want to calculate the force that is applicable on this one due to this one, then you have to use this vector. So the force acting on this one due to this one will be directed to in this direction. So that is what it is written, that F12 is the force on body 1 due to body 2 is equal to opposite of the force on body 2 due to body 1. That's what it means. And this is simply related G into M1, M2 into this is ER is the vector directed along this side and divided by R square, where R is the distance between them. This is not a vector. So I have put a unit vector here. So this is the magnitude of this vector R. And gravitational field, acceleration due to gravity, as you can see, it is calculated from this stuff, that is G into m mass of Earth divided by R square. And actually it is more or less constant near the surface of the Earth, but then when you go much away from it, it will change. It will not remain the same as it is. For general purpose mechanics and all, we use this as constant, that is 9.81 meter per second square. Here I have written it meters per second, but it is actually meters per second square. And G is the universal gravitational constant. As you can see that this is meter cube per kilogram per second square. And the gravitational field lines, as you can see near the surface of the Earth, you can see that these are more or less parallel. Whereas if you look at from a far distance, you can see that they are they are not parallel. They actually look like this. Now, the important thing is you can calculate the gravitational field, intensity of gravitational field by counting the number of lines in that local area. For example, here you can see that in this one, if I take a count from here to here in a straight line, you will see the number is same as if I take a count from here to here. But in this case, if I take a count from within a small distance, you will see that the number of field lines will increase as you move towards the center. So that also shows that this is also another measure with which you can actually find what is the intensity. The gravitational potential is always negative, and it's because it's attractive, and if you can derive it from the gravitational field, the relation holds by integration and differentiation. So if you integrate the gravitational field, you will get gravitational potential, and from that negative sign arises. This is also this small v. This is the acceleration due to gravity. You can express this as delta A v by delta r. Now, then next comes the Kepler's laws of planetary motion. This is very simple actually. There are three laws. One says that every planets move around the sun in elliptical orbits with sun at one of its focus. And the second law says that while orbiting a planet, sweep out equal areas in equal times. And the third law states that the square of planet's period is proportional to the cube of its mean distance from the sun. Now, these laws are applicable to artificially launched satellites or any other two-body system where there are two bodies, one body encircling the other. Now, I will show you what it is actually. The first law shows that, see, this is an ellipse. This is an ellipse in which a planet moves, and there are two focus for an ellipse. You can see the distance at this point, from this point to this point, and the distance from this point to this point. If you add these two distance, you take any point on this will be same. That is the description of an ellipse. Now here you can see that the sun can be at this or this. Anyway, we are considering here it is, and the planet revolves around the sun. This is the first law of Kepler. The second law states that the planet sweeps equal areas in equal times. That means if this is your sun, and if this planet is encircling it in an orbit, then you can see that for a particular time interval delta t, the area swept is equal to the area of this one. This is the shaded area is the area swept by the planet in time delta t. Here you can see that again this area has to be same, that is A1 should be equal to A2. But then here it covers a larger distance, whereas it covers a smaller distance. That means near the perihelion, when the planet comes near the perihelion, its speed increases, whereas when it goes to the aphelion, that is the farthest point from the sun, its speed will decrease. So this is governed by Kepler's second law. Now we come to the Kepler's third law. Now here it is just to calculate the period of the revolution. So you can relate it using Newton's laws of gravitation. So here you can see that this gmm by r square, that is Newton's law of force. So what I am doing is the gravitational force between these two bodies because of gravitational attraction should be equal to the centripetal force. The centripetal force is caused when you move a body around something, so it tries to go away from it. So the acceleration is centripetal towards the center. So now if we relate these two, then only they will be in equilibrium. So this is the gravitational part and this is the centripetal part. Now omega square r, omega square, the velocity, instantaneous velocity of the body when you rotate it in this direction, that is tangential to the circle, will be equal to omega into r, where omega is the radians per second or revolutions per second, you can take it in a general sense. So revolution per unit time, and that into this distance will give you the velocity in this direction, because then it will become a meters per second, something like that, which will be your, yes. So now mv square by 2, half the centripetal part we are putting it here. Now from this equation you can simplify it and you can get that omega square is equal to gm by r cube, where r is this distance. And from this you can further simplify by putting omega is equal to 2 pi by t, where t is the time period, and then you can finally obtain this one. The actual, this is a simple expression. Here you won't get the actual equation is this one. This is a simple way with which you can derive, and this is quite fairly accurate, because in actual expression the mass of the planet is negligible as compared to the mass of the sun. So this can be approximated to that. But then the actual formula can be derived from a two-body problem, and this is what you get in the this is the actual formula for the orbital time period. Now, if you look at the solar system, then Kepler discovered the planet goes in elliptical orbits with sun at one focus. Also, all planets revolve in the same direction, which is counterclockwise as seen from north. So if you see the top view if you consider the north pole of the Earth, if you go in that direction much above the sky, and from there if you look into the solar system, you can see that the orbits are in this direction. This is the direction of rotation, if you see from the top, from the northern side. And this is in the scale. This is drawn to the scale, except that the sun size has not been put up, and also the planet size has not been put up to scale. Only the orbits are shown here on scale. Now, if we take the inner planets, that is from Mars onwards to the sun, you can see it here, and so you can see the orbits. So actually we say that the orbits are elliptical. Elliptical not in very good sense, because the eccentricity is very, very less. So it's more or less circular, but still there is some eccentricity in the ellipse. So these are not actually circles, but these are ellipses with very little bit of eccentricity. Pluto is not considered a planet anymore. That you know, because of obvious reasons, that it does not follow. It's not in the same plane of the solar system, and it has got very high eccentricity. So that's why they have removed the name of Pluto. Now there are other type of orbits like the binary star orbit, where you see that two bodies, two suns or two stars rotate around one another. So the actual center of mass is here. this is the orbit of this particular star, and this is the orbit of another this particular star. So they move around encircling this center of mass. And you will be very wondering, astonished to know that more than 80% of the stars in our galaxy are binaries. Our sun is of course not in a binary configuration. Now coming back to the gravitation, here when we launch a satellite, we need to know what is the escape velocity at which the satellite has to be put up, so that it goes into it goes out of the gravitational. I mean, it should not come back to Earth. That's what I mean. So that is called the escape velocity. It is about 7 miles per second or something like that for Earth. So the escape velocity means that if you throw an object from the Earth with a velocity less than this escape velocity, it will return back to Earth. But if you throw something which at escape or slightly greater than escape velocity, it will escape from the Earth and it will never return to Earth. And this is calculated by equating the kinetic energy to the potential energy. So this half mv square is the kinetic energy, and the potential energy is gmm by r. The force was gmm by r square. So when you integrate it, you get gmm by r. So this is energy. So when you equate it finally, and this will be equated at the escape velocity. That is, you have to apply that much amount of kinetic energy so that the object overcomes the potential energy and comes out of it. The potential energy means gravitational potential energy. So that how much velocity you have to apply, that is the escape velocity, and from this relation you can simply get this one as 2 gmm by r under root. This is used for artificial satellite launching. Now we go into the electromagnetics. So this will be useful for any wave property of electromagnetic waves. In general, electromagnetic waves consist of electric and magnetic fields, and both of them are having the same frequency. There may be, we will see if there is any phase difference between them or not, or other things, but they have to be in same frequency and they have to be orthogonal to each other. We will go into the Maxwell's equations for deriving the field equations, but before that the definitions are here. E is the electric field, it is a vector in volts per meter. H is magnetic field in amperes per meter. Rho is the charge density in coulomb per meter cube. Epsilon 0 is the permittivity of free space. This is the value, farad per meter, and mu naught is the permeability of free space, and this is the value. Now D is also called the electric flux density. So this is related to the electric field by this constant epsilon naught, the permittivity. And similarly, the magnetic flux density B is related to the magnetic field H with this constant, this mu naught. These two are fixed. Epsilon naught and mu naught stands for the values in free space. Now, James Clerk Maxwell unified the laws of electricity and magnetism into 4 well-defined equations. These became the foundation of the classical electromagnetic theory. Now, these are the 4 equations. This is the dot product. I hope everybody knows about vectors and vector calculus to some extent, so they can understand this. This particular thing, you can express it as I into dou by dou x plus j into dou by dou y plus k into dou by dou z, and this d can be expressed as I into dx plus j into dy plus k into dz. These are the various components in x, y, z directions, and this one is equal to rho. This is the charge density, whereas the magnetic field is equal to 0. Now here comes one question which I think many people may be knowing or may not have thought about it. That is, people have seen that the electric field lines always ends up with some source. That is, if there is an electric field line, it never closes without a source. So if there is, for example, if you take a battery, you can connect the wire around it, and the circuit will be complete through the wire. So the source is the battery, and the field, you can say, it goes around the wire. Whereas magnetic field lines are closed, so they don't have any source inside it. So this equation represents that del dot B is equal to 0. Whereas here you can see that there requires a charge density inside. And these are the cross equations, that is del cross E is equal to time differentiation of the B. And del cross H is equal to time differentiation of electric flux density plus J. Now J is called the conduction current, whereas this particular thing is called the displacement current. In free space, the conduction current, I think people must be knowing it. That is, if you have a, you can compare a resistor and a capacitor. In a resistor, the current will flow directly through the body. Whereas in a capacitor, although you can say the plates are isolated, but still a charge will flow through that, and that is the displacement current. The current is caused by the displacement in the capacitor, whereas in a resistor it is because of the conduction, the conductivity of the material. The same thing happens in free space. If it is, if there is some, the medium is lossy kind of thing, so there has to be conduction current, and if the medium is non-lossy, then it has to be a displacement current. And the displacement current is occurs only when there is a change of field. That is what it says, that the time differentiation. This has to be differentiated with time. So there should be some change in the displacement in D. Then only this displacement current will come with respect to time. Now for electromagnetic waves, we just take the, in the previous equation, that del cross E, in this we will put one more del and cross it with this one, and when we express it, you can follow the general rules of vector calculus, and you can finally get that this expression, this left hand side can be equated to this, and this is equal to this one. On the other hand, you can take a time differentiation of the other Maxwell's equation, and you can get this, and after simplification you will get this one. So how you derive it is not very important, but the result that you get is important. Here, this is it. So every equation, you see that there is a term 1 by c square and a double differentiation, partial differentiation with respect to time. So this is the spatial derivative, and this is the time derivative. So and also they are the second derivatives. So this is the interesting part in wave equation. It means that if there is a change of the field along a distance, there has to be a change of the field due to time also, and this is what it means. Means that if you equate this one with this one, you just take it on the other side, you will see that a double differentiative change along a direction is equal to the double differentiative change of the field with time. So from this you can, if you solve this equation, you will see that it has to be a traveling wave, and this c is a constant. This is the this is not a vector, this is a scalar. This is the speed of light, and that is calculated from this one, this expression for free space. If you are not in free space, if you have some dielectric or anything, so you can multiply this mu naught with mu r and epsilon naught with epsilon r. Similarly, we get the other wave equation. This is for E, and here we get for H. And then it looks very similar to the previous one. And again, you can see that we get this C as same. And if you calculate C, it will be equal to 3 into 10 to the power 8 meters per second, which is the speed of light. I have written it velocity, but it should be actually speed of light. It's a scalar quantity. Now, if you see the spherical wave, if you have a point source, if you are near to the point source, you will see that the energy diverts, it just keeps on radiating in various directions. So, if you want to see a wavefront means a area in which you will see for any instant of time the phases of all the points in that area should be same. So what I mean is, you can understand here. See, if you see over a time, this wave has traveled in this direction, and at this wave from the same source has traveled in this direction, and so on. So for after an interval of say, let us say delta t, you come to this point. So here, if you see what is the phase of this wave, you will see it has the same phase here, and the same phase here, and the same phase here, and so on. And the same thing will occur at a distance of lambda. Lambda is one wavelength. After one wavelength also, you will see that the same value of electric field here has to be same here. Of course, for this it will not be, because the wave has diverted and the energy is spread out. So it will not be the case, but we will see that in plane waves. So all I mean to say that the phases across this line for the waves are constant. So this is called the wavefront. Here also, and in between you will have several lines where you will see the phases are same. Now, you don't get plane waves from a nearer source. You usually get it from a, you can approximate it. In fact, I believe that there is no plane wave at all. To some extent, it has to be spherical wave. Spherical in the sense means you can see that this surface is spherical. And from spherical waves, you can construct a plane wave. If you go to a large distance, then you can see that instead of a spherical surface, you have a planar surface. So here, if you calculate the electric field here, it has to be same here, same here, same here, provided these are separated by a distance of one wavelength. And the energy doesn't divert and the wave crosses as it is. So there has to be a large distance of separation between this. For example, the signals that we get from the astronomical objects, they are very large, and so we consider them to be more or less plane waves over a short region of space. Now, if you go to the solution for the Maxwell's equation or wave equations, you can see that we already derived these two, and then if you substitute these this vector value as E naught into e to the power I into k dot r, this is a dot product, minus omega t, then you will see that this equation will be satisfied with this kind of solution. That is something which has a variation in space and which has a variation in time. The time variation is due to a frequency. It has to be a periodic wave. This omega t represents that, and then it has to be traveling at a constant speed. So this is what it means, and this is the magnitude of the thing which you can increase or decrease depending on your choice. Similarly, the same kind of equation holds for this one. You only replace E naught by H naught, and the equations are same. But you can add a phase shift of delta. That is what we want to see, that if there is really any phase shift between the electric and magnetic fields. And this value of k is equal to 2 pi by lambda, is called the wave number. We have introduced a negative or positive phase difference delta between E and H. Later we shall show that delta has to be 0 or plus minus 2 pi, etc. So we have to, there is a transverse relation, as I said, that they are in 90 degrees to each other. You can take this Maxwell's equation and you can expand this one in this form, and then the right hand side, this part, you can expand it in this form. And when you equate the two, you will see an expression that is k cross E is equal to omega mu naught H. So K cross K is traveling in a direction perpendicular to K and perpendicular to E, where E is the electric field. The electric field and the direction of propagation, perpendicular to the electric field and the direction of propagation. That is what it means. So H has to be perpendicular to the direction of propagation and also has to be perpendicular to the electric field. Similarly, you get another expression for this, where you can see that the magnetic field has to be perpendicular, the electric field has to be perpendicular to the direction of propagation and the magnetic field. And then we can show from the other two scalar Maxwell's equation that this, we want to find out these two expressions. These are the two expressions we want to find out. And this is a dot product. Dot product stays along the same direction, and it's a scalar quantity. So you can see the dot product of the direction of propagation and the electric field is 0. Hence E is perpendicular to K. So E has to be perpendicular to K. Otherwise, if it is in the same direction, it will be 0. And another inference we get from this one, that H has to be perpendicular to K. So with all these hints, we can finally construct the picture of a electromagnetic wave. So you can see that this is the direction in which the wave is propagating. So I am putting it as K, and this is E, and this is B. So you can see that electric field is like this, whereas the magnetic field is like this, and there is a orthogonality between them. When the electric field decreases, the magnetic field also decreases. When they are 0, they are 0. The electric field increases in opposite direction, the magnetic field also increases in opposite direction, and so on. So they are proportional and they are attached to each other. That is what it means. Now we have to see that whether this has to be on this side or on the other side. I think I have, here it is. See, here E and B I have interchanged here, E and B. So that means this has gone to the other side. So this is also another possibility in which you can see. But these will be, this will be restricted by the other laws of physics, that whether to accept this one or this one. Now we come to the irradiance, that is called the energy per unit volume. So this is the energy density stored in an electric field. This is a simple equation, you can calculate it. I am not going into much details. So this is the energy density, and this is equal to simply half epsilon naught E square. If you remember, half CV square for the capacitor, energy stored in a capacitor, or half Li square for the energy stored in inductor, where I is the current and L is the inductance. So this, you can see that this equation looks very similar to that. So this is half epsilon naught E square, and the magnetic energy will be half epsilon naught H square, and the total energy will be the energy content in the wave, because you have both magnetic and electric fields. So this is the total energy. So this is the energy density, not energy. I am confusing you. This is energy density because you have field here. It has to be in a volume. Then only it will be that energy. So I am energy per unit volume. So it is energy density. So the total energy density will be the sum of electric and magnetic field densities, energy densities, and this is what it comes out. This can be epsilon naught E square or mu naught H square. So this half and half term goes out, and you can simply get it epsilon naught E square and mu naught H square. Now, if E is equal to this particular expression, omega t plus phi, and omega is very large, the time average of E is obtained as, okay, what I am trying to say is that the wave will be fluctuating, so at any instant of time the energy of the wave will be different. So you need to calculate the energy over a period of time, and that is called the average value. Now average of what? If you take the average of a wave, if it is a zero shift, then it will be 0. So you have to calculate the mean square average. So this is the mean square average. I think these equations everybody has solved during their engineering, and I don't know in BSc and all they solve these equations or not. So you are just calculating the mean square value of this, and you will see that E naught square by 2. This is the mean square value of this. And the mean total energy U density may be expressed in terms of peak of E as shown below. So this is equal to half epsilon, this is the same expression as that. Now you take a cube like this. The cube has 3 faces, this and the top one. Now if you see what we want, what we are interested is, we are interested in passing a wave through this, and we are interested in this wave will come out from in this direction, and we are interested to see that how much energy per unit time is crossing this surface. That is what we are interested. So if we take the length of the cube as c into delta t, where c is the speed of the wave and delta t is the time interval in which you want to see, and this area A, you can see that the amount of energy psi passing through the surface area A of the cube in time delta t is equal to the average value, mean square value, into c into delta t. So you can see from the geometry it actually fits. So c delta t is here, and this is the area of this one, and this is the energy density. So if you multiply these 3, you will get that. The power passing through area per unit volume is given by, so this energy divided by the delta t will be the power. Power is always equal to energy per unit time. So now if we define irradiance or intensity I as the power per unit area, which may be expressed as I is equal to P by A. So finally what you get is, these are the expressions, this one. This it's coming to the same, epsilon naught E square, you can see, and here we have put this speed of light, and this is what is called the intensity. So intensity is same as the power density, except that you have put up a value of C here, and this also is equal to 1 by 2 Z naught, where Z naught is the intrinsic impedance, you can say, of free space, and the phase velocity is calculated by C by N, where N is the refractive index. These things, some of these things you have to remember. You cannot derive every time, so you have to remember some of these expressions, and substituting this in this, you get that the intensity can be expressed in terms of phase velocity and electric field. So finally we come to this Poynting vector. It says that in an isotopic medium, energy flows along the direction of propagation. The magnitude and direction of this flow is given by the Poynting vector. See, this is the Poynting vector, S. S is equal to E cross H, very simple to remember. And this is, if you calculate it, its unit should be watts per meter square, but it is a vector, because it propagates. The energy is propagating in a direction, so it is a vector. And this is, you can say that when you are looking, you are collecting some power of a wave by using a dish of aperture area something. So you need to calculate what is the power that will be collected. So there comes the area, and that is related with this one, A into S. A is the area of the dish, into S will give you the amount of power that you measure, because S will be in A will be in meter square. So this will go, and you will get finally the wattage out of that one. So the application is there. The corresponding intensity of irradiance is given by I is equal to, this is the again the mean value, and this is again the mean value of this, and this the mean value of this is equal to the mean value of that. Finally, you get that the Poynting vector is normal to E and H. Of course, it has to be in the direction of propagation. The Poynting vector has be, see, the Poynting vector will always be in this direction. So this is perpendicular to E and H. E is in this direction, H is in this direction. The propagation energy propagation takes place in this direction. That is what it means. And this is actually the cross product of this and this. So if you using the vector algebra, if you just take the cross product of this will be along this direction, and that is what it means. This S is equal to E cross H. And then when we are calculating the irradiance, you calculate it over a period of time. And finally, you get this scalar values as S is equal to C epsilon naught E square. You can read it out. I am not going to read it. Now, we want to understand what is polarization. In this example, I have tried to draw as best as I could so that people can understand polarization. Of course, people with there are many people from different backgrounds, so I need to explain this one. I just get it in recording mode so that my voice will get recorded in this one, so I get it, but then I will expect a call from somewhere. Because I'm recording this screen. You can see this one. This is the screen I'm trying to record it. So my desktop, we have good sound recording with this now, so I thought that I would record it here. Anyway. So here you can see the polarization of an electromagnetic wave. Now we are dropping out one of the components of electromagnetic waves, that is, we are dropping the magnetic component, which is orthogonal to the electric field component. So we are just dropping it out, and we will do our analysis only in the electric field. Now, if you have a wave, if this is your x and y axis, and you are looking from here, you are sitting at this axis or looking through the axis, and the wave is traveling in this direction. Now, if you have a wave that has started at time t and it has propagated like this, alongside you have another wave which is orthogonal to this one, but they are both electric fields, they are propagating in this direction. The resultant is you create another wave that is the vector sum of these two waves. Now, for any instant of time, for example, what is the value here? It is equal to the just vector sum of these two vectors. This is the one. So, if you look from here, what you will see over a period of time, for at particular time instant t1, you will see the electric field vector is in this direction. Now, this has to be 45 degrees because we have kept this and this magnitude same. So, at time t1, you will see that this is like this. After some time, you will see that it is increasing. As you can see, this wave is increasing here. And then after some time, you will see it is decreasing. And after some time, you will see that it has vanished. And then after some time, you will see it is increasing in the negative direction. That is this one, and so on. So, this is what you will see. These are at the different intervals. And the components of E along X and Y are always in phase. In this example, the magnitudes are also so much. I have told you. So, this is called a linear polarization. Linear in the sense means if you see this plane in which the resultant wave comes, this plane never changes. It's only the magnitude of this vector changes, but the direction, okay, the direction reverses. I will not say the direction doesn't change. The only thing is that it lies in the same plane. Now we come to a circular or special helical polarization. Now, in the previous example, if you see, here there is no phase difference between this wave and this wave, and so the resultant wave has to be in the same plane. But here what we did is, we put up a phase difference between one of the waves with the other. So, if you add this one, these two waves instantaneous values, and you are observing from here, you will see that this vector, because of addition of these two, will rotate. For example, here I have added this first particular vector as t1. You will see that time instant t1, you will see that. Here this one is there, whereas the value of the yellow one is 0, so it has to be this way. In this
in between these, you will see that the green one exists as well as the yellow one exists, so it is 45 degrees. So this vector has moved from this position to this position over a period of time. And again, if we go on like this, you will see that it will travel as a helix. But what you will see from here is this one. You will see that this vector will be rotating, and it will rotate in either left direction or towards right direction. And depending on that, you can call it as left circular or right circular. So this instance, when you see from here, you can see at instant T1 it is like this, T2 it is like this, and so on. And you can see it is rotating in this way. So you can call it as a left circular polarization. Now this circular polarization can be changed into elliptical polarization if you change either the phase between these two and or the magnitudes of these two. But there has to be a phase difference between these two. If it is 90 degree and the phases are the amplitudes of these waves are same, then that will result to this circular polarization. If you change the magnitude of one of these, then it will be an elliptical. What is meant by elliptical is this will not be circular anymore. It will become an ellipse like this, because one of the magnitudes is more. Now these are the expressions. If the electric field rotates like a right-handed screw as seen from the source, it is right circular. As I said that you have to define the circularity of the polarization along the direction of the propagation. That is, you have to consider yourself sitting at the source and you see the source, it is moving, and you have to see whether it moves towards left side or right side. Depending on that, you can categorize it as left or right. So these are the two expressions that comes out. This has to be 90 degrees. Now if you change the E0 of Ey by some amount, it will be still like that, except that it will be a elliptical polarization. I have not given a diagram for this. There is other way of looking at into elliptical polarization is you can change this theta here. And the locus of the vector, you will see that it will be an ellipse. Locus means this vector, you can see it will be moving along this path. And this is for the circular. Now there is one more thing called random polarization. Now most of the astronomical signals that comes to us, they have a random polarization. Random means if plane of polarization is not fixed to one plane, or it does not behave in a well-defined form. Like it will not be a circular or elliptical, something like that. It will keep on changing with time. And a good example you have is some of these bulbs or any light source you see, unless it is called a polarized light, you will see that they have a random nature of polarization. So this diagram explains it, that the plane of polarization in which the vector lies, that is going to shift in different directions for different times. So it's not well defined. So I will read the properties here. The plane of electric field and so the magnetic field are random functions of time. The probability of orientation of the electric field in any direction in the xy plane is same. That means you can expect the electric field to be wherever you want. You will see the probability of the occurring of the electric field in that direction is same as you go into another direction and you try to find out electric field there. The magnitude of electric field and so the magnetic field at any instant of time is always same. This is a instrument which is called wide grid polarizer, and I just explain it. It is like a grating. If you might have done grating experiments, and you must be knowing how grating works. So we have taken a source here which has a random polarization. This polarization is in any direction, and it is propagating along this direction. Now if you keep wires vertically like this, this is a you can call it as a grating, you have kept wires like this. So the polarization that is parallel to the wire, that part will be absorbed by this or whatever it is. It will not allow that part to pass, whereas the part that is perpendicular to this will be allowed to pass, and that is what you can see here. Now, the classical electromagnetic theory explains that light excites the electrons to move along the wires, which then emit light that cancels the input light. The polarization perpendicular to the wire are unaffected. So that is the classical explanation for this one. Now, you must know also what is Malus law, because many times we do for heat characterization. These are very basic things. I will go into much more details when we enter into the technological part of it, where I will explain it in more detail. But these are very basic things which people in technical line or engineering background, they should know when they are working in this place. So I am just trying to refresh their memories. Now, here we have tried to relate the polarization properties with angle. So, what we want to mean, what we mean that is, if we have a single polarization and we measure the power at an angle not the same as that angle in which the polarization sits, so we should know what power we should get from there. So the experiment is like this. Here there is a light source which has a random polarization, and then we have a polarizer which will allow, like in previous, this is a polarizer, you can say. Here you can see the polarization will be along this direction. That means it will allow only this component, that is this component, to pass through it, and then we pass it through an analyzer. The analyzer will allow only this component to pass. This angle is theta. We want to measure the power at an angle theta. So you simply you can see that from the observer's point, you can see that this is the thing that is from this diagram. You can see that this is what you are getting, and if you relate it, this is equal to I is equal to I naught cos square theta. So theta is this angle. So I is the intensity, and that is why it is the square function. So that means if you move this polarizer to 90 degrees, you will get this. You will not get anything, because this cos of theta will be will go away. Now again we are going into some of the concepts of classical electromagnetic theory. If an electromagnetic radiation falls on charged particles, for example plasma, and if the mass of these individual particles are very small, for example electrons, the particles absorb these waves and move up and down along the polarization of the wave at the frequency of incoming radiation. This gives rise to a secondary emission in all directions. Okay. So what it means that if you have a charged particle, and if you are subjecting it to an electromagnetic wave, and you think that the charged particle has very small mass, so that its inertia is less and it can be moved easily. So this wave that is falling on that one will cause it to oscillate. In the process of oscillation, it will again radiate because it is oscillating. The oscillating charge always radiates. So this is it. We see an incident wave falling on an electron. The electron will be oscillating in this direction, because the polarization is in this way, and then again, because it is oscillating in this direction, again it will emit something in the same polarized way. Now, classically, we don't expect any change of wavelength. That is, the input wavelength should be equal to the output wavelength, but this is not true. We will see it later. The classical electromagnetic theory doesn't explain that one. Now, change in wavelength of scattered light is completely unexpected classically. However, we shall see later that it is possible to have a changed wavelength in quantum scattering. Now, it is the same diagram. We are seeing it in more details. We have a source here, and we have an oscillating electron here, and the source polarization is along this direction, so the electron will be oscillating in this direction. Now you see what is the power that is radiated, if there is any radiation along this direction. You see, yes, it is there, and the polarization is still vertical. Here if you see, you will still get a emitted radiation from this one, because it is oscillating, again it will be vertical. Here also it will be, and here also it will be. But on the top you don't see anything, because the oscillation is in this direction, so you don't get that. If you change the orientation of this, you will see at this point you will not see the output. Whereas for any other side you will see, because the oscillations are along these directions. So the summary is the direction of oscillation of charges, the radial distance and the vector and radial distance vector and polarization lies in the same plane. And the polarization of radiated field is always perpendicular to the radial distance vector. I think should we stop here for a cup of tea, or we want to continue with this? Yeah. So we just stop here for some time.
So we will go to the next slide. So far we have seen for a single polarization. Now we see for multiple polarization or randomly polarized thing. If a light falls on this kind of particle and it makes it oscillate in random directions, this is what happens. You will be observing everything at every place, except that in this plane you will observe only single polarization. The reason you can think about it, the oscillation will be in this plane. So it has to capture anything in this plane, and it has to be in one direction only. Here also it is like this. But if you see here, it sees the oscillation in different directions. It is able to see the other dimension it is getting. So you can see here. But relatively this will be smaller. Whereas here it will be same as this one. It is a particle. It is a particle in which a plasma particle, you can say. In plasma, some electrons, you can say. You can take one electron is there. I am just showing for that. Yeah, you're right. Now, this I will not explain in details. This is what is happening, that the sun rays are falling on the Earth's atmosphere, and where it is in a plasma form or slightly lower and other places, it is exciting the particles in different directions, and that is the reason you see a polarized kind of thing here, and it depends on the time and also the angle in which you are looking. If anybody wants, I can tell them in more details. I don't think it is of much relevance here. So this is another thing which people are knowing in electromagnetics, that is Faraday rotation. And here you can see this experiment consists of a source here and a place where you want to find what is the polarization angle change. The wave has to travel through a medium. This is a medium, and this medium has to be has to have a magnetic field. Now it says that Faraday effect or Faraday rotation is a magneto-optical phenomena. It causes a rotation of the plane of polarization which is linearly proportional to the component of magnetic field in the direction of propagation. So the wave is traveling in this direction. The tilt, the wave front will tilt, and the tilt is proportional to the magnetic field. And here is the formula, that is the angle of rotation beta in radians is proportional to the product of magnetic field B. B should be measured in Tesla with length of the path. This is the length of the path, and D in meters. So this is the equation. This is a constant, and this is called the Verdat constant of the material. Now, radiation, we are defining it. Radiation is an energy in the form of electromagnetic waves or particulate matter traveling in air or free space. Of course, radiation can be passing through medium also, dielectric medium, so we are not denying that, but here we are considering as free space. A classification of radiation, it can be ionizing radiation or non-ionizing radiation. Now, ionizing radiation means it is a high energy electromagnetic wave or heavy particles beta and alpha are high enough energy to pull electron from orbit. That is, if this radiation hits some atoms and all, it will be able to remove the electrons from orbit, some electrons, and it will change the property of that material. Non-ionizing radiation, you must be knowing about work function and all. All these things are related. That work function depends on the frequency above which it will cause it to emit electrons. At lower frequency, even if you increase the intensity, it will not be able to do that one. So these are there the ionization takes place. I'm not going in details to that experiment. Non-ionization radiation, it is the lower energy electromagnetic waves, not enough energy to pull the electron from the orbit, but it can excite the electrons. Okay. So in an atom, if you put up this energy, then there will be some disturbance. This is the classical model. I am talking about the something like Bohr's atomic model. I am not going into the quantum mechanics and all. That if we require, we can see later. So it says about that model. Not enough energy to pull electron from orbit, but it can excite the electron. Excitation means if it has to move up and down, depending on based on the frequency of the incoming waves. Now this is the electromagnetic spectrum. This is a very bad diagram. I have to draw it actually. This is something I collected from the internet. So this is in angstrom units. This is a wavelength, and here is our region of visible light. You can see it has a very narrow spectrum. The radio spectrum is quite broad. This is gamma rays, X-rays, extreme ultraviolet, and so on. And our sensitivity in wavelengths, if you see that 400 to 700 nanometers, and we get a peak around this value. So this is the sensitivity of the eye. And these are very simple but important things. This is the reflection of light. If it is a plane surface, it will reflect back, and the angle of incidence should be equal to the angle of reflection. Angle of incidence is counted with respect to the surface. Now, if the surface is not a smooth surface, the reflection will take place in different directions. So this is what you can expect from a radiating source. If it is coming to an antenna, it can hit the ground and then it will come as a radio frequency interference, and you will not be able to know the polarization or any kind of, it will be totally disturbed because of the things that are existing. It's not a plain ground. So the laws of optics also are used in radio astronomy. For our purpose, for radio waves to be reflected, the ground has to be conducting, or the reflector material has to be conducting. Since ground is a conductor, it reflects. Now, reflection of light. This also, you know that these are two material mediums. This is one medium, and this is another medium. I think this is a school level thing I am talking about. And this is the perpendicular line drawn across this. And this is the incident angle, and this is measured with the normal. This is called the normal. And this is the wave that is traveling in this direction inside the second medium. These N1 and N2 are the refractive indices. This is the reflected ray. So the Snell's law, if you see, these are mu is equal to sin I by sin R or something like that. This is what it is actually. The reflected ray lies in a plane of incidence and has an angle theta 2. Yeah, this is theta 2. Yeah, of refraction, and that is related to the angle of incidence theta 1. N2 sin theta 2 is equal to N1 sin theta 1. The symbols N1 and N2 are dimensionless constants called the index of refraction. Index of refraction is for a material is equal to these expressions. People should memorize this. This should be equal to the speed of light divided by the phase velocity. these laws are also applicable to radio waves. So, here comes another thing that is called Brewster angle. Is very important. If an incident light enters into a region having an interface of two different refractive indices, and then it bends because this is more denser than this one, and the bending should be such that this angle, that is the angle in which it has to reflect back. Suppose if it is a plane surface and it is a reflective surface, this wave will get reflected here. It is not a reflecting surface, but still some amount still gets reflected from this, and most of this are collected here. It goes inside. But if you want to absolutely stop this one, then you have to send this ray following this Brewster angle. The Brewster angle says that the angle between this and this should be equal to 90 degrees. You have to focus this in such a way that the reflected angle, this one, or I will give you the equations here, this theta I plus theta t has to be equal to 90 degrees. Brewster angle is the angle of incidence at which the light with a particular polarization is perfectly transmitted to the surface with no reflection. That is what it means. And you can have all sort of relations like this one. You can relate it with the refractive indices of the materials. This is the total internal reflection. If you have a light source here, this is something like water here, and this is something like air here, rarer medium and denser medium. The light, if you pass it straight, it goes out. If you bend it, you will see that some portion gets inside and some portion goes, and then gradually it happens like this. And at a particular angle here, this is called the critical angle or critical case, at which the light doesn't go out, because in the rarer medium, when the light bends away from the normal, if you draw a normal here, this angle, it has to be bending away from the normal, because you are entering from denser to rarer medium. This bending has to be such that it has to be exactly 90 degrees, or it has to be along the surface. So this is called the critical case. So you use this kind of things in fiber optics and all, where you use the total internal reflection, and this is what it is. A wave in a tube, inside a tube, you have to fix the outside and inside values of n such that, and also the thickness of the tube that will define this angle, and you can pass a ray without getting the ray out of it. That is what is a fiber. So here it shows an actual diagram where you have an aquarium or something like that, and you have lights. So it is bending, and here it is the total internal reflection. That is this actual experiment. You can find it in Wikipedia or somewhere. So these are the expressions for that. This critical angle is equal to n2 by n1 sine inverse of that. Now this is called dispersion. Dispersion is the bending of light when you change the medium from one medium to another, and which depends on the wavelength. And in a prism, you can see the dispersion. The white light is dispersed into several colors, and I call it as it's the Fourier transform of that. You are showing the spectrum of that one. So that's how I call that one. So this is like taking Fourier transform of white light. So white light enters. See, these are having different wavelengths, with different colors. So they move inside the medium. The refraction occurs in at different angles, and so they spread out. Now this is what it is actually. If you see for particular wavelength, and if you calculate the index of refraction, it will be changing. The index of refraction n in different material is different for same wavelength of light. The index of refraction n is in same material is different for different wavelengths of light. Now we come to the particle type of behaviors or something like that. Light can be treated as particles or waves depending upon applications. In quantum scattering and all, you can see it will be treated as a particle. The particle nature of light is called photons. the mass of a photon is 0, the photon has momentum p. I mean, you call p as the momentum of a photon. You will use this variable. Now, light is also taught as electromagnetic waves, and there you get the wave nature of the light by using the Young's double slit experiment. You can show that light behaves as waves, whereas by Compton's experiment you can show that light behaves as particles. So light interference experiments are related to waves. Now, these are some of the formulas. I think people may not be very much interested in this, but still I will talk about it. Some of the simple formulas which people can remember. This C is equal to lambda nu, where nu is the frequency, C is the speed of light, and lambda is the wavelength. Wavelength in meters, speed in meters per second, and nu is frequency in hertz. Energy and frequency of a radiation, you can calculate it as h into nu, where nu is the frequency and h is Planck's constant. This is the value for this. And energy momentum is equal to P into C. Relativistic energy and momentum. Yeah, this is very important because you know the physicists, as I heard somebody was telling that for some particular particle they have discovered some mass, whereas in these places we have not. We consider it is massless particle, and if you calculate the relativistic energy and momentum, you will see that E square is equal to P square C square plus M square C4, where C is again the speed of light, M is the mass. In this expression, we calculate the energy of particles moving at relativistic speeds. Since the mass of a photon is 0, if we substitute in this, we get the energy of the photon. Momentum and frequency, h by lambda, h nu by c, and this sometimes instead of h you use h bar, where h bar is equal to h bar upon 2 pi. K is called the wave number, that's 2 pi by lambda. Yeah, now we come to Compton scattering. Here we consider the light as a photon particle. Now, we have a electron here, and we want it to be hit by another particle, and it will hit it, and it will cause this particle to go in some direction, and the particle that was hitting will also move in another direction. And we have to relate the energy and the momentum to get what is the change and so on that we will see. So here is an electron, the incoming photon hits it. After hitting, the electron moves in this direction, this is called the scattered electron, and the scattered photon goes in this direction, this angle is theta. So we have P nu dash is the scattered photon's momentum, and PE is the scattered electron's momentum. So using these two, conservation of energy and conservation of momentum, you have to relate the previous momentum and momentum after that should be equal to each other, and previous energy and energy after that, the total energy of the system should be equal. So that is what we are doing. The ME is the mass of electron. In nu dash you can see that this is the radiation after scattering. And when you actually relate these two equations, you get the change in wavelength. That is, the wave was coming with some wavelength, or the photon has some wavelength, and that when you, after the hitting of it, it has a different wavelength here. So what is the change? The change in wavelength is equal to previous wavelength and the current wavelength, and that is related to h upon MEC into 1 minus cos theta, where theta is this one. So this experiment was done in several materials, and they were able to relate this one. That time it is a very long back story, and there they found the particle nature of light. Now Broglie was another person who actually was in his PhD thesis, he just changed the expression of Einstein. That is P is equal to h by lambda. He changed it to lambda is equal to h by P. And the prediction was we should see different diffraction and interference of matter waves. So I am not going much into all of this. This is called the de Broglie wavelength. Yeah. This is an important concept which people should know. This something like phased arrays and all. You can produce a planar wave using phased arrays. So the concept comes from here. It is very similar to that. I find it similar. I don't know what other people will say. This is called the Huygens-Fresnel principle, or how you spell it, I don't know. I think it is Huygens. So here is a slit, and here is a plane waves that are coming to it. At this point, you can think that this plane wave consists of small isotopic sources. Each one are separate sources, and when the waves from each of these are added up, they again produce another plane wave. That is what it says. So here we have considered this place as consisting of this many things, and from the diagram you can see when you add them, the interference adds up to produce a wave like this, which we have seen is true. So what it means is that the Huygens principle concludes that any wavefront can be broken up into small particles, emitting particles. And here you can see in a refraction the same thing happens. You can see this is the plane in which it is coming. These are the planes, wavefronts of the waves. And after this, when it enters in, the interference will cause it, and again the planes will become like this. So this I think is very simple. You add two waves here. This is the result. This is the result of this, and adding these two in different phases. Okay. Now we go to interference of light. Interference of light is the superposition of two light waves, or it can be many light waves. It need not be two. Two is for simpler case. If two waves are of same frequency, a fringe pattern consisting of maxima and minima of intensities will form depending on the phase differences of the waves at the point of interaction. The two waves can come from a single source or from different sources. So these points are very important, that they have to be from of the same frequency, and they can be produced from either from the same source or from two different sources, but the frequency should be same. And we consider I1 and I2 are the intensities of the two waves, and the phase of each wave is represented as phi1 with respect to a fixed point. With respect to fixed point, the phase of one wave is phi1, the phase of another wave is phi2. So this equation is very easy to remember. You can relate the intensities as the total intensity I is equal to the intensity of 1 and the intensity of 2 plus the intensity of 2 and so on. Into here it is important that this cos phi2 minus phi1, and this part actually behaves cosinusoidally, and this is what you can see that depending on this phase differences between these two, you will get a net change in value of this one. There is a fixed term. These two are causing the fixed terms. They do not change. This term, you can see that they become positive and negative. So they can make this one go up and down. So this is responsible for a fringe-like pattern. Interference of light showed that light is a wave, not particle. That's what we started with. And there are two famous experiments: Thomas-Young's double slit experiment and Michelson's interferometer. So we go for the wave properties now, and this is the Young's double slit experiment. So here you can see that there is a plane wave coming from far, and it has to be of single frequency. It cannot be of many frequencies. You will not see interference. For example, if you try this experiment with a white light, you will not be able to see. But if you try it with a laser, you will be able to see. So now these are plane waves. These are coming, and there is a object which has a slit here. So this slit will act as another source, and it will radiate. Again, you cut two slits here, and they will act as again 2 point sources. This one, these two, and at a distance, some distance, we have a screen here, and we want to interfere one source S1 with the other one, and we want to see what happens on this screen. So here you can see that these are the wavefronts that are drawn. This is something complicated, and somewhere there are maximas and somewhere there are minimas. So the minimas are these lines are the minimas, these dashed lines, where you have minimum intensity, and maximas are this one where they add up in phase. Minimas are where they cancel each other. As a result, if you see on this one, you will see that white and dark patches. This is called the interference fringes. But you have to know that this has to be monochromatic. That is of same wavelength. You cannot have multiple wavelengths, and you cannot get a fringe here. Now we go to the expressions. This is one source, this is another source. This is separated by distance d, and this particular distance is d sin theta. N is an integer, and lambda is the wavelength, and d is this distance. Okay. So the maxima condition occurs when d sin theta is equal to n lambda. And this capital D is the distance on the screen. So what you will see is, you will see a interference pattern. The intensity will be maximum here, and of course there will be intensity here, but then again you will see it is not same. As I showed in the earlier one, we couldn't estimate that, but here you can estimate it using these equations. That is what it means. And the total intensity on the screen, again you can see this consists of I1 plus I2 plus this term plus cos of this thing. So this particular thing, this causes the nature to vary like this particular term in this one. Now we have another interferometer. These two are important because once we measure cross correlation and once we measure the autocorrelation. So these two interferometers actually simulate that. So that is why I thought that it is better to bring these things in that. The spatial coherence and temporal coherence that we will see later. So in this Michelson interferometer, the interferometer, here you have a source here. Here there is a partially reflecting mirror, and we have another mirror. This is fully reflecting. We have another mirror. This is fully reflecting. Now this mirror, there is a arrangement with which you can move the mirror along this direction. And here there is a telescope, or eyepiece, I will say, not telescope. Eyepiece will see what is the result of this. So what will happen? The ray will go from here. It will travel a distance L after getting reflected and come back, and it will pass through. The same ray, some portion of it will again travel a distance L. This is the distance L, same as this, and then we have an adjustable distance which is user specified, and after that it will reflect from here, and again it will come here. So these two waves, that is coming from this mirror and the other way from this mirror, they will interfere here, and you want to see what is the interference. So by increasing or decreasing this distance, you can make them to go in phase and out of phase. So here you can see you are using the same source, and you are causing the interference between these two. Whereas in the previous one, you are using two different sources. Although they may be derived from same source, but they are from different. So they are separated in space. So again, the expression is here for this Michelson-Morley. Michelson-Morley experiment is something different. I did not talk about it here. This one is okay. This is the same expression as in the previous one. Again, you can see that this is the part which is responsible for this fringe. This D. D is this distance. If you vary this distance, you will say maxima, minima, and all. Now, coherence and visibility is interference. Now you can see this is a bulb here, and the filament of this bulb is not a point, but it is distributed over some region of space. So each point on this bulb filament will radiate, and also radiating in a spectrum of white light, let us say. Of course, bulb radiates more in the red infrared region also, which we are not able to see in the infrared region. It develops a lot of heat, I mean to say that. But anyway, we consider it in the white region itself. And you can see that it generates a lot of waves, each of these points. And they are of different colors, means they are of different frequencies. So they are not these phases of this, the wavefronts of one emission is not parallel to the wavefront of another emission. So these are called incoherent. When you pass it through a pinhole, instead of a filament, you have a point source here, and there you can see that these wavefronts may be of different frequencies, but they are spatially coherent. See, there is an equal difference between that. Now when we pass it through a filter, this will actually cut it into a single wavelength, and it will reduce other wavelengths, remove other wavelengths. Of course, that's our sort of filter is difficult to make, which will give you some laser-like kind of thing. But anyway, here we assume it like that. And then here you have the wavefronts. Again, they are equally spaced because they are having same frequency. All other frequencies are removed. Only one frequency is kept here. So this is called coherent. Whereas spatially coherent means the wavefront has to maintain same spatial relation with the other wavefronts. That is called spatially coherent. And actual coherence means they should be uniform. Means the distance between each wavefront should be same. That happens when you have a single frequency. So I will just read out this one. Coherence is a wave property that enables stationary interference. Two waves are coherent if they have same constant relative phase. The degree of coherence is a measure of how perfectly the waves can cancel due to destructive interference. The degree of coherence is proportional to the interference visibility. Okay. Now we are gradually relating it with all the visibility and interference of what is it actually. So if you remember this, recall that I1 and I2 are the intensities of two waves, phi1 and phi2 are their respective phases, and the resultant intensity I at the point of superposition is given as the sum of these two and this variable term. This is a fixed term, this is a variable term. Fixed term consisting of intensity of two sources and variable term due to phase difference. Now we consider this both the intensities of peak intensities of both the sources are considered as same here, I0, and the equation simplifies to this one. Now if the light source is extended over an angle alpha, now in this, as I said, that consider a bulb-like filament where you have a filament like this, which is acting as your light source. So the angle from this is alpha. So you are extending it like that. So instead of if the light source is extended over an angle alpha, instead of a point, we get this function. This new thing that has been added is this portion, this sync function, and this will further modify this fringe pattern. So note that in all these cases discussed so far, we see a fixed term and a variable term. Also note that the variable term is different for different cases. The variable term is responsible for the fringe and is related to the coherence and visibility. This relation, we will still strengthen this relationship. What is coherence and visibility? I think these are going to be slightly dirty here. No, because expressions are there. People do not like much of expressions. I know that. Okay. So coherence and visibility in interference. Just take out, just grasp as much as possible. Otherwise, you leave it. It is not. You need not know all these things. That is also not. Okay. Anyway. The coherence C12 is related to the time average of electric fields E1 and E2 of the two waves, and cos phi2 minus phi1 is equal to 1. In general, this expression, this bracket shows the time average. As I said earlier, that you have to take a time average of this, and that is equal to this one into C12. But C12 is the time average of this. Now you remember this C12 expression. You just this is very important because these are related to the visibilities what we collect. There can be three cases of C12 as described below. C12 is equal to 1, so it is called perfectly coherent. This. Both waves have same frequency. So in this case, you can see that, for example, we have both waves having same frequencies. If you you are just expressing this into that, and then you will see that I1 is equal to A1 square, I2 is equal to A2 square, and hence this reduces to this expression. So therefore it indicates that C12 has to be 1. That is only when the two frequencies are exactly same, then this one is equal to 1. It means that. And this is called perfectly coherent. Whereas perfectly incoherent means that this expression has to be 0. That means the variable term has to go off. So this occurs when both waves have different frequencies, and you have two different frequencies, and you substitute it, and you get this time average becomes 0. So C12 is 0 here. And then there is a partial coherence. This means that when more than one frequency but common in both waves. So this happens when you don't get C12 exactly equal to 1 or C12 not equal to 0 but in between. So in this example you can put it as omega 1 plus omega 2 as the first one source frequencies, and here is omega 1 plus omega 2 plus phi 2 we are putting it up, and finally you get that this factor C12 is equal to, coherence factor C12 is equal to 0.5. So what it means that the coherence factor actually is something which we want to know. If we want to relate two sources, we want to know what is the like features between them. That is what we do when we measure, when we collect the data in the observatory, we collect the visibility. So in optics, this is how it is related. So again, if you see this, the coherence C12 is proportional to the fringe contrast, which is known as visibility V. You might have heard this term more people discussing and all. This is the thing, that the visibility V is equal to maximum intensity minus minimum intensity divided by maximum intensity plus minimum intensity. This looks like VSWR expression turned over. Here it varies from 0 to 1, whereas VSWR 1 to infinity. So if you just reverse that one, then you will get this kind of expression. So this visibility is nothing but over this, the intensity distribution, you find out what is maximum intensity, minimum intensity, and then you calculate it. And this visibility is proportional to the coherence. So visibility ranges from 0 to 1, and the higher visibility, better the fringe contrast. Coherence can be of two types. Okay. After discussing this, here this is I max and this I minima. Now we go for the properties. There are two types you can say. One is temporal coherence and another is spatial coherence. So as I said that we discussed two interferometers, one with the space and one with the time. Time means same source, whereas the space means two different sources. So these two are simulating them. So temporal coherence means coherence of two waves derived from a single source with time delay between them, where phi 2 minus phi 1 is constant. For example, the Michelson interferometer. Whereas spatial coherence, coherence of two sources separated in space at same time measured the center of the screen, at the center of the screen, where this term is equal to 1. So this is similar to Young's double slit experiment. Now you can see this one diagrammatically. This will be easier to understand. The temporal coherence is the time the wave fronts remains equally spaced. So you see this diagram in which you will see that there are different wave fronts. One is for maxima and one is for minima for the whatever it is. So here you see in this region where it is marked, you can see that these are equally spaced. The spacings are equal. Whereas beyond this region, here you can see that it is not like that, and also here you will see the spacing has reduced and reduced. But whereas between these this place the spacings are same. Between these two, if you see between these two. So this is called temporal coherence time, tau c. This one, this region. This is the time during which we maintain the equal distance of wave front. That is the coherence time. Whereas the coherence length is something like this. Suppose you have some source and its wavefront looks like this a peculiar kind of wavefront. Somewhere it is arbitrary. But here you can see that they are maintaining equal distances between them. Maybe it can be a temporal coherence will be there because they are maintaining equal distances. But what about along this direction? Along this direction you see that it varies. But here in this small region you can see that it is more or less straight. And this length is called the coherence length. So since there are two transverse dimensions, we can define a coherent area. That means the wavefront is a two-dimensional thing, one along x-axis and one along y-axis, and then they form an area. So the instead of coherence length, we can we have to see coherence area also. So now again, these are some examples. Light beam can be fully or partially coherent in both time and space. Light beams can be fully or partially coherent in both time and space. Okay. So there can be full coherence in time as well as in space. Now in this first example shows spatial coherence and also temporal coherence. So in the time domain, if you see along this direction, if you see they are equally spaced, so they have a temporal coherence. Along this direction, you see that they are straight, so they have a spatial coherence. Here in this example, you can see that they have a temporal coherence. Here is temporal coherence and spatial incoherence, because you see that these are not straight. This cannot form an area over which it is constant. So it is not. Then again, in this example, you can see that this is a spatial coherence but temporal incoherence. Temporal incoherence because you can see that they are not in the time, they are not uniform, whereas along the spatial side they are. And in this diagram, you see both of them are not occurring. That spatial incoherence and temporal incoherence. Here you can see that there is nothing along this direction which is constant, or nothing along the time axis where it maintains that. I think with this you get a lot of idea about what is coherence and all. Then we are defining some of these things like coherence time. So this is a definition, but you can get something out of this definition. For example, in this you can see if delta nu, this is the coherence time, if delta nu is the bandwidth of light and the coherence time tau c, it is the reciprocal of this bandwidth. That means the coherence time will be equal to 1 by delta nu. So that means the more you filter out unwanted frequencies and you concentrate to one frequency, this becomes this particular delta nu becomes smaller and tends to 0, and so the coherence time becomes very high. So lasers, for example, lasers have long coherence times, about 1 second, and that is greater than 10 to the power 14 cycles. It is amazing because you have a very accurate frequency. And then again, here we define coherence length. It is the propagation distance L from a coherent source to a point where an electromagnetic wave maintains a specified degree of coherence. So we have seen that one. So the expression is L is equal to C is speed of light and delta nu is the wavelength. Lasers have a long coherence length, and this is about 3 into 10 to the power 8 meters. That's also amazing. Coherence area, if d is the diameter of the source observed at a distance d, then the Van Sitter-Zernike theorem, this we will know about it when we go into the techniques in later lectures. I will talk about this. States that the spatial coherence area AC is d square lambda square by pi d square. This is the spatial coherence area. This is the source. The wave fronts smoothen out as they propagate from the source. For example, this is the source here, and these are the wave fronts. Here you can see near the source, you can see that they are following the nature of this. But if you go at a very large distance and take a smaller area, of course this much area at a larger distance will correct only a point of this. So there you will see that it has flattened out. So radio interferometers, the two signals are derived from a point on the radio source. That is as you can see in the interferometers, one Michelson and another is the Young's double slit experiment. We have signals here. It says that the two signals are derived from a point on the radio source. The radio source is a distant source which we are observing. Instead of a laser beam splitting, two antennas look at point source, look at a point on the source. That is, since in the previous diagram we have seen that if you go much far away, we will see only a small portion of this, and which will be like a point. So that is what it is saying. Instead of a movable mirror, electronic time delay is used. Okay, in interferometer we have seen that we are adjusting manually the distance from the fringe. Here, instead of that, in radio interferometers we use a delay here. This is the time delay which is introduced. This is as good as shifting the phase or moving it. The visibility function is the time average of the cross products of the two antenna outputs. So the visibility function is the time average between the signal that is coming from this antenna and this antenna, averaged over time, and that is called the integration time. You see that they call it as 16 seconds or something like that. We have it here. It's generally used for, but there are other settings also. They can change that one. Now we define the cross correlation and autocorrelation. Cross correlation is the spatial coherence, Young's double slit experiment. Spatial coherence means from two separate points, and autocorrelation is the temporal coherence, which is the Michelson's interferometer. So this is very important because this is the very basic background of radio astronomy, which I don't know, most of the people do not discuss about this one. Now there are very simple things like Doppler effect, which you must be knowing it. I think I am on to the end of my slide. This is a Doppler effect, and there are two terms which astronomers use. One is called blue shift, another is called the red shift. So it's very simple. If you are moving along this direction and making a sound, this observer here will hear it at higher frequency, whereas this observer will hear your sound at lower frequency. So this observer will get a blue shift and this observer will get a red shift. And this is related here mathematically. This lambda is the frequency, and the light from a moving source is blue or red shifted by Z. Z is called the shift. You can say red shift or blue shift depending on its value. Lambda minus lambda naught by lambda naught. Lambda is the source wavelength, and lambda naught is the I think one should be actually received wavelength and another should be the emitted wavelength. I think I have not written it properly here. I think this is the emitted wavelength and this is the received wavelength. That's what I think it is. Delta lambda is the wavelength change due to Doppler effect, and this is the change in wavelength. It may emit at some wavelength, but you receive at a different wavelength, and the change in wavelength is delta lambda. This is it, lambda minus lambda naught. And VR is the radial velocity along the line of sight. You will come to a next diagram where things will become more easier. Not this, the other one after this. So in astronomy we apply this Doppler shift. For other I mean for general use also Doppler shift is very important. For example, people monitor the speed of vehicles. You might have seen polices and all, they use it. So Doppler shifts are applicable. Doppler radars, many places in engineering we use that one. In astronomy there is one application where they use this one. That is Doppler effect can be used to measure the components of source velocity towards the observer if the source emission wavelength is known. Suppose you know the, suppose on Earth you are observing this source here. This source is moving along this direction V. So it will create two components. This vector can be broken up into this plus this. So you have a movement along this direction, you have a movement along this direction. Now to the Doppler shift that you get in the Earth about the wavelength of this one, this component doesn't play any role because this is perpendicular to you. Only this component, whether it is coming towards you or going away from you, that decides the Doppler shift, and depending on that you get a red shift or blue shift. Here is an example. Here there is an observer, there is a binary orbit, and okay, there are this object is moving. I think the diagram is not properly shown here, so I cannot relate it much with this one. And finally, this is it. Even the diagram is self-explanatory, and I think this is the last slide. I think we are coming to this is the last slide. So here there are two stars, not two stars. One star at two different positions, A and B. You are observing here. So when the star's position is here, it has a component towards you. It is approaching you, and this A gives you a blue shift here. Whereas here it is going away from you, it gives a red shift. In this position it also gives a blue shift, and in this position it gives a red shift because it has some component along this direction and it has some component along your direction. Whereas here they have no component towards you, there is no velocity towards you. So when the stars move perpendicular out of line of sight, there are no Doppler shifts. That's what it says. And similarly, you can get these two diagrams also. Spectral lines shifting apart and then merging are the signs of spectroscopic binary. So this requires a little bit of explanation that some of the wavelengths that we supposed to have been generated by different elements in hot object or existing at very different at very extreme large distances. So we want to measure such things, like there may be a star-like thing which is in a binary rotation or something like that, and we know that the star color O, B, A, F, G, these are the classification of stars depending on their temperature and their spectral lines. They are classified. Depending on that, we can find the wavelength in which the stars can radiate because of the materials inside it, and also the color of the star. And then we can find out its orbit by calculating the Doppler shift over a period of observation when the star completes at least half of its cycle around the other star. And also various elements also in space, like supernova explosion and all, gaseous nebulae and all, many of the things, hydrogen, if they are moving or what velocity it is, or a distance object which is moving away from us, if we know a spectral emission line, we can catch it here. If it is redshifted, the redshifted can be significantly high if the object is very large, so that the optical wavelength gets translated into radio wavelengths when we measure here. And this is like something like that CMB, the cosmic microwave background radiation, where you see today its temperature is 2.73 degree Kelvin, but actually the time when it was radiated, it was very high, so you receive it in radio. So these are some of the things. Of course, the CMB is not because of Doppler shift. It is called the expansion of space. But in space expansion, in both way they are related. They cause change in frequencies. So with this, I think I come to the end of this lecture. Thank you very much. And if you have any questions.